Hello, everyone. Welcome to the MIT Faculty Forum. I am Dianna Cowern. I'm an MIT alumni 2011, and I will serve as moderator for this discussion. I am the host of Physics Girl, which is a YouTube channel about physics, all things physics, hands-on demonstrations, questions about the universe and dark matter. And I started that in an effort to engage more with the public about physics and get people, the general public and kids interested in science. So that's what I do, and I will be moderating this discussion, this forum about graphene. So as a reminder, we welcome your questions during this chat. For MIT alumni joining us via Zoom, please use the Q&A feature at the bottom of your screen to submit questions. And for everyone else listening on YouTube, you can add your questions in the comment field. And we also encourage you to tweet using the hashtag MIT Better World and @thephysicsgirl, which is my handle. I'll be checking those questions. And we'll get to as many questions as we can for our panelists. So today we're going to hear from 3 different alumni who will share some of their current projects and research on graphene. So we're going to start with an overview from each of the panelists, catching up on their career since leaving MIT, and then talking about their current projects. So if we could start with, let me just real quick introduce all of them, and then we'll start with, one by one. So we've got with us Dr. Paul Weiss, Dr. Evan Reed, and Dr. Jari Kinaret. So let's start with Dr. Paul Weiss, if you could go through your research and give us a good overview. You'll have to unmute your microphone.
Right, exactly, thank you.
Wonderful.
Yes?
Yeah, you were good.
Okay, great. So our group looks at the ultimate limits of miniaturization, the smallest switches and motors in the world. And to do that, we developed 2 capabilities. One is the placement of individual molecules and assemblies into controlled environments. And the second is microscopes that measure structure, function, and spectra all at the same time. And we can do that many tens and hundreds of thousands of times to understand these functional molecules and functional assemblies. What we learned along the way is that we can use the microscopes to map the orbitals and really explore the chemistry at the atomic scale the way an atom or molecule probing a surface would do. And where that maps into graphene, in particular and other 2-dimensional materials, is that we try and create perfect contacts where the molecular orbitals, the electronic properties, the optical properties, the mechanical properties are preserved across those connections. Right now, as you're going to hear, graphene has amazing properties because the chemistry is such that all the alternating double and single bonds make these resonant strong structures that allow incredible electron mobility and so forth. But the way we make contact to those materials is really stupid. We evaporate metal on top of them, destroying the properties is one option. And the second way that people do it is they take chemistry to destroy the double bonds so that they can make connections to the graphene and then react to those sites that have become available for further chemistry, but again, that destroys the properties. So what we argue is that we should leverage a century of organic chemistry. Some of you remember 541, 542, might have been renamed by now. I took those pass-fail way back when, and now I'm forced to go back and relearn much of that, or at least collaborate with some of the people who taught me in those classes 100 years ago. And what we try to do then is design connections and design the chemistry so that across those contacts, we preserve not only the molecular orbitals and the band structure, but we avoid nodes. You'll remember the difference between, for instance, an s and a p orbital is there's a node right at the nucleus for a p orbital. We don't want those nodes in a contact because that would prevent the electronic connection from working properly. So we see that as one of the biggest opportunities, not just for graphene, but for other materials where we can align the bands, we can reduce the resistance of contacts, and we can preserve those properties. And that's been our focus in this area. And we can continue on with some other parts later.
Great, thank you. Yeah, great. Thank you, Dr. Weiss. Next, we'll move on to Dr. Jari Kinaret.
Hello. I have a couple of slides that I prepared, so maybe I'll show them so that I remember what I was planning to say. And somewhere here, there is the full screen option. Here. So my name is Jari Kinaret. I'm originally from Finland. I got my master's degrees in theoretical physics and electrical engineering there in the late 80s. And then I moved to MIT as a Fulbright fellow, got my PhD in physics in 92. After that, my wife and I, we moved to Europe. She had never lived in Europe. She also got her PhD in physics at MIT. So we spent a couple of years in Copenhagen, and since 95, I'm in Gothenburg in Sweden, professor at Chalmers University of Technology, at different kinds of functions like director of nanoscience and nanotechnology. And now I'm the director of the Graphene Flagship, which I will describe in the next few pages. When I have time to do research, I focus on theoretical nanoscience, most recently mechanical and optical properties of graphene. And so what is this Graphene Flagship that I mentioned? It's something that is called the Future and Emerging Technology Flagship, or FET Flagship. It's a very large research program, a 10-year project period. We started October 1st, 2013. We have a overall project budget of 1 billion euros. By today's exchange rate, something like $1.2 billion. Half of that comes from the European Commission. The other half comes from other sources, member states, and participating organizations, and so on. So today we are 156 partners in 23 countries across Europe. About 1/3 of them are from industry, about 1/2 are academic, and the remaining 1/6 are other kinds of partners like research institutes and so on. And this whole project is coordinated from Chalmers. Gothenburg is indicated on the map there. And we are about 450 full-time equivalent persons working on this. Hardly anybody spends all of their time on the flagship, so we are altogether something like 1,300 individuals. And in addition, we have something that we call associated members who collaborate with us, but are funded through different channels. And so what we do is that we try to complete the entire value chain that is needed to make graphene a technology. And I should say that it's not only graphene, it's also related 2D materials. It's just too complicated to call it a graphene and related 2D materials flagship. So we started by looking at production techniques. Now we are in the phase where most of our effort is spent on developing components, which might be solar cells or fast lasers or composite materials and so on. And as time moves along, we are moving more and more into system integration. We already do that a little bit, for instance, with Airbus and some electronics companies. An example of what we have accomplished, I took a slide that describes our exhibition at the Mobile World Congress. It's a very large meeting that is organized yearly. This one was in Barcelona, with something like 120,000 visitors. We have our own pavilion where the eye catcher was this car that you see that contains graphene composites produced by the University of Manchester together with the BAC company. You also see some products that have already emerged from the project, such as the motorcycle helmet. Next to the motorcycle helmet, there is a retina implant where we use graphene as a material to electrically stimulate a damaged retina so that people who would otherwise be blind have the ability to at least read large text. Then there is a little electronic gadget, which is a part of a photo or optical modulator that allows transmission speeds of up to 10 gigabits per second. It's a collaboration between the Ericsson and Nokia company with a couple of other groups in the project. And the last little item is a flexible and transceiver chip developed by AMO company in Aachen in Germany, which can be used in many Internet of Things kind of applications. And the colorful picture underneath is a special exhibit where we targeted the school children in Barcelona. It was quite well liked. And I think the last slide connects a little bit to the topic of this discussion. It's about evolution of disruptive technologies. Initially, when you get an idea or somebody gets an idea, people get excited and they think it's going to solve all world's problems. It's this increasing expectations, and at some point realism starts to kick in and you realize that, well, maybe it didn't cure cancer after all, but it's good for some things, and we are probably now in that phase where the expectations when it comes to graphene are becoming more realistic. And as time moves along, some things become profitable. We already have a number of profitable products, but some things like maybe electronic applications are still very much in the lab phase. So that pretty much covers what I had to say as an introduction.
Great, thank you, Dr. Kinaret. And we will move on to our third and last panelist, Dr. Reed.
Oh, thanks, Diana. So I did my PhD at MIT in the physics department, course 8, within the group of Professor John Joannopoulos. And then I moved to Lawrence Livermore National Lab for about 5 years. I've had a great time there. And about 7 or 8 years ago, moved to the Material Science and Engineering Department at Stanford University, where our group is engaged in trying to predict properties of materials. So we do theory and modeling to try to identify opportunities and guide experimentalists toward interesting experiments. And there's a thread within our group that focuses on 2D materials, and we also do some machine learning, trying to adapt ideas from machine learning to try to predict properties of materials, in addition to a few others. And I have a few slides here to show. First, I'll share my screen. Oops. So the focus of this is on graphene, but it's worth mentioning, and Jari mentioned this briefly, that there actually, since the discovery of graphene, there have been also discoveries of a spectrum of other very thin materials, not necessarily quite a single layer thick, but still very thin nonetheless, materials that are chemically relatively stable. And there have been a few databases proposed for these, and generally the consensus seems to be there around 1,000 of these other materials. And it's worth, in addition to graphene, talking a little bit about these too, because there's a very broad spectrum of properties that may be useful for a broader spectrum of applications than just graphene. And so graphene, of course, is atomically thin, but many of these are a little bit thicker. Like this cadmium compound is about 10 atoms thick or so. Like graphene, it comes from a bulk 3D structure. It comes from a 3D crystal structure. And there are a variety of morphologies. So here's a vanadium compound on the right here that has perforations in it. So it has holes in it, unlike graphene. And so graphene is a good electrical conductor, But for many applications, you don't necessarily want a good conductor. You want something with a band gap, like for a transistor type of application. Ideally, you want a semiconductor with a electronic band gap. And so this is just an estimate of the distribution of the electronic band gap for this spectrum of about 1,000 materials. And there are many other materials that are down here at 0, which corresponds to reasonably good electrical conductors like graphene. But there's also a spectrum that have band gaps within the optical regime. So if you want to make an optoelectronic kind of device, there's a spectrum of materials available for you to do that. If you want to have a material that's electrically insulating for electronic applications, there's also a pretty broad spectrum of materials that have very large electronic gaps. So it looks like, beyond graphene, there's actually a relatively full spectrum of properties of these very thin, chemically stable materials. And there are even materials that have been either synthesized or mined that have they're bulk 3D crystals, but they consist of layers that are chemically distinct. So in graphene, of course, comes from the graphite structure, and within graphite, all of the layers are chemically identical. They're all graphene layers. But there's some materials that are starting to be discovered that actually consist of 2 chemically distinct layers. And these are interesting for a variety of applications. Most of the action in functional materials and devices occurs at interfaces. And these materials are essentially just very large interfaces between 2 very thin types of 2D materials. I also just want to mention briefly one of the potential applications for these materials. So one of the most common questions I'm asked is, so what's special about these? What can you really do with a very thin material that you couldn't do with, say, a bulk material? And one of the of course, there are many answers to that, but just one of the interesting effects that emerges in many cases at this atomically thin limit is called the piezoelectric effect. And this is an effect whereby if you apply an electric field to some material, you can generate a mechanical response in the form of a strain. And this is an effect that's used behind the scenes in lots of applications. It's used for strain sensors. It's used in your phones. It's also used for some inkjet printers to actually squirt the ink onto the page. It's used in a variety of places. And there's always a drive for new types of piezoelectric materials. And some years ago, we actually had a student who appreciated that many of these 2D materials should be piezoelectric. He thought they actually exhibit this effect. And so he calculated the magnitude of this effect. And the surprise was that it turns out to be comparable in magnitude to many bulk 3D materials like aluminum nitride here. So it should be big enough to be useful for devices and be observed. And in fact, a few years later, there were a number of experiments reporting this effect, including strain type sensors on a flexible substrate. If you put one of these 2D materials on a flexible substrate and you bend it, you can actually observe a voltage across the material, and it comprises a useful strain sensor. And it turns out many of these materials exhibit this effect. We think there are a few hundred of these. And so this is really these thin materials are really a new class of piezoelectric materials. You essentially need to discover a new type of crystal structure to identify a new piezoelectric material. And that's essentially what these atomically thin materials are. They're new types of crystal structures with symmetry and other properties that are completely distinct from the bulk 3D structures from which they come. And in fact, many of these piezoelectric 2D materials come from bulk materials that are in fact not piezoelectric. So they're not obvious places to look for this effect. But it turns out when you single out one layer or one component of these materials, they exhibit this effect. So it's something that really only emerges at the 2D limit. And it's a case where you absolutely have to have this 2D nature of these materials to exhibit the effect.
Great. Thank you so much for that. It's nice to see the paths that MIT alumni have taken. It seems like most of them have gone to California since leaving MIT. And to see the different applications of graphene. So I want to go onto that for just a second. One of the questions we received from Twitter from Reen Sugar was, what applications besides computers are there for graphene? For example, using graphene for desalination. And it sounds like we've gone over some of these applications in the overviews, but if anyone wants to take the question of how graphene is applied in different industries, what are some of the other uses of graphene?
Well, I can try to answer that. The range of applications is very wide, and actually the first products that are on the market are usually right now composite materials. So I showed the example of this motorcycle helmet, but there is a lot of other composite materials. There are also people working very hard on graphene in battery applications and supercapacitors. There are companies that have products on that. So actually the electronics products are the slowest ones to come to market, in part because the demands on materials quality are very high, and also because silicon technology is so well established that it's very tough to compete with that. So there are many other applications. Somebody asked about water purification. There are several different approaches to that, both in Europe and in the US, but I'm not aware of any product on the market yet in that field.
Great. And Dr. Weiss, you have more to add on applications.
Right. So as Evan mentioned, one of the keys is controlling electronic properties, what would give us the ability to desalinate or use graphene as a filter, controlled holes. People know now how to make fairly uncontrolled pores, but in fact we can build up even precise structures with precise holes if we go for that strategy. And a number of groups are trying to do that, notably Klaus Mühlen his whole institute in Germany devoted to how do we make precursors that give us the ultimate structures that we're after. One of the other applications takes advantage of mechanical properties. So we have a startup that's trying to make speakers and earphones out of graphene. They're sort of uniform spectral properties, both optically and acoustically, that we can take advantage of for graphene, and as well as some other 2D materials. Evan brought up another interesting point, and that is you can stack these materials, and they don't have to be homogeneous stacks. So one of the more interesting aspects is, take all the very large number of materials that he mentioned, and now imagine combinations. When you put them together, there are also exciting properties. And in addition to just a simple stack, you have to worry about the tilt angle between the layers that one puts together, and that'll give different properties as well. That's one thing. We don't know how to do it all in terms of manufacturing, so there's going to be a whole engineering and sort of nano-manufacturing side to creating useful applications by controlling those stacking properties.
Great. Along the same line of questioning, Mariana is interested in knowing if she's interested in graphene applications in water quality sensors, point of use testing, starting with heavy metals. So she's wondering if there are any specific organizations working on this application for water quality sensors.
When it comes to water quality sensors, I'm not aware of that. Like I mentioned, there are different approaches to water purification. For instance, a company called Technalia or University of Manchester recently published some work, and I think Lockheed Martin was one of the first, actually based on some work that was done at MIT. But specifically for water quality sensors, I'm not aware of that.
Okay, great. Another question, I like this one. An anonymous attendee asked, is graphene factoring into the hunt for the first truly quantum computer? Dr. Reed, do you have Any input on this one?
I'm not aware, I'm just not aware of substantive work in that area. There are a lot of calculations, but in terms of experimental things, I haven't seen anything. I wouldn't be necessarily aware of it if there was something.
Yeah, I think most of the research on quantum computers at this point is coming from physics and not from material science. But I think it's a fun question nonetheless. There was another question from Twitter. Can graphene be produced without fossil fuels, for example, from regular glucose or cellulose? As a non-chemist, I'm not sure if this is, I'm not sure what exactly this question is asking.
Sure.
But
yeah. I think I could take this one. So one of my roles, I'm editor of ACS Nano, one of the leading nanoscience journals, and some time ago, we published a paper from Jim Tour at Weiss showing you could use all kinds of things that contain carbon to make graphene. That includes cockroaches, Girl Scout cookies, and dog shit. So you don't need fossil fuels in that sense.
Yeah, I've heard work where they studied from Belgian chocolate, and I personally think there are better uses for Belgian chocolate than to make graphene.
I agree with that.
I'm gonna ask a question of my own, because I'm sure some of our listeners are like me, don't have a strong chemistry or material science background. You were mentioning 541 and 542, the organic chemistry that I never took. I just took course 8 classes and course 6, some of those electrical engineering classes. So how I want to know some of the basics on how graphene is produced. I've heard some stories about Scotch tape. I'm also curious for these other materials that are very thin materials made from a base 3D structure, if those are produced using Scotch tape. So just how is graphene made? How are some of these other very thin materials made?
Okay, well, there are many ways of making graphene. There are ways where you essentially start from graphite. Graphite is basically layers of graphene on top of each other, and you apply some kind of a violence to get these layers apart. It can be physical violence, or it can be chemical violence. What happens in this process is that the layers break, so you get small flakes. So those are good for things like composite materials. If you want to make high quality electronics, you do the other way, that you start from anything that contains carbon. You heat it up so that the carbon atoms separate from the rest, and then you can use chemical vapor deposition techniques. For instance, on copper, they fall on a copper surface and build graphene layers. You can also start by silicon carbide and heat it even higher temperature so that the silicon atoms evaporate and they leave a graphene layer on the surface. So there are several different techniques, some of which you could actually do in your own kitchen to produce graphene. So it's not a particularly complicated production process.
So it sounds like the complicatedness of the production process really has to do with how pure your sample needs to be, exactly, or how good the structure needs to be. It seems like a lot of the questions we're getting are still about specific applications. So there's a question. Well, we just answered the question from Phil Richardson about what base material you're using to produce your graphene from. So it's graphite. That's the base 3D structure, it sounds like, for some of these instances. One question is about research of graphene tubes in photovoltaics. Another question is about medical applications for graphene. So I think people are interested in these specific applications. If any of you can speak to these exciting and interesting applications in medicine and photovoltaics.
You know, the advantage in the photovoltaic side is that the absorption of graphene is flat. In other words, it does not vary across the visible and near visible spectrum. So unlike other materials where there are a lot of features in the spectrum, you have to take those into account. While the absorption of graphene is small for a single layer, it's a couple of percent, it's at least uniform. And because of the electronic properties, then one can make fast detectors if that's, if that's what you're after. And in terms of medical applications, the graphene itself may not have as interesting properties other than that, might not be terribly reactive, but the derivatives where one adds functional groups to it or decorates the edges certainly interacts biologically. I mean, one of the most exciting things about nanoscience is that the scale matches the functional scale in biology. And so we can make little pieces of graphene decorated with other species that then interacts biologically. Now, that's sort of good and bad. Right? And the more difficult part may be making those sufficiently precise so that, number one, they have the effects that we want, and number two, they're possible to get through regulation. I mean, if usually we want a very precise, for therapeutic, for instance, we want a very precise structure, and so we have to be able to make that. Graphene may not be the optimal choice in that sense.
Great. One of the most recent questions that came in from Cyril is, what is the main challenge in using graphene in actual products? As a non-expert, I would guess that it's an atom thick. So that sounds complicated to work with for many reasons. But what is the main challenge, or some of the main challenges in using graphene in actual products?
Well, many of the challenges nowadays are beginning to be in the sort of manufacturing process. There was another question about these composite materials. Do you need specific size of the flakes so that they disperse well? The answer is yes. What size you need depends on the polymer that you use as the host material, where you put graphene as additives. But these kinds of composite applications are relatively straightforward. I can pretty much guarantee that if you take a 15-minute walk from MIT, you can already buy graphene products, mostly in different kinds of sports equipment, from anything from bicycles to alpine skis and so on. The electronics things are harder because you need to get a very high yield to match the rest of the process.
Thank you. Mariana asked another question. What is the most exciting application each of the panelists have seen in their experience so far? So continuing on with applications. Dr. Reed, do you want to start?
Yeah, I think my sense is that the applications are still very much emerging, and just say, anecdotally, I was at a plastics conference, plastics engineers conference recently, and it was a very applied setting. It was very few academics there, and it was mostly representatives from companies. And there was a whole session devoted to specifically this. It was, how do we use graphene? How do we get it into our products? And what is it useful for? And one of the emerging themes from that session, there were a lot of companies trying to integrate graphene or kind of graphitic forms of carbon into their plastics, with the goal of tailoring some of its properties, either its mechanical properties or electronic properties. And it turned out that there were some advantages to doing this, which were not necessarily based on the properties. There actually may be manufacturing advantages. And one of the companies was claiming that they actually could bring their manufacturing costs down just by introducing graphitic carbon into their manufacturing process. And so it was just interesting to kind of see these very unexpected commercial advantages and applications for this material. That was certainly not expected. I don't think a lot of people are thinking about the kind of manufacturing advantages of this material. Mostly focused on the properties. So it's not clear, it takes a couple decades for new materials to really kind of reach maturity and get into products. And and for the people in those product spaces to really learn about it and what it can do and what it can't do. And so I think that's just kind of continually evolving.
Yeah, I totally agree with Evan that we're still very much in the exploration phase. The really exciting part is going into this world where no one's ever been, and finding new properties. And as he showed, not just in graphene, but in many other two-dimensional materials, there are all kinds of things that we're discovering that we'll have to sort those out. We have some touchstones of three-dimensional materials and films and so forth that we grow now, and we make those comparisons. But making the jump from, okay, here are these intrinsic properties of the material that give us some hope that we can make new electronics or new filters for desalination, something else. While those properties are there, we haven't done the scale up of the properties, and we haven't really seen how they're going to shake out as we put together larger structures. I'll give you one example. When you put graphene down on a metal surface, sometimes it completely passivates the metal and prevents chemistry, and sometimes it appears invisible chemically. And we haven't sorted out when those two situations, which one of those is going to occur in a particular case. So understanding those kinds of basic science questions will let us evolve the material and the applications into something that we can manufacture. They'll be interesting and useful and hopefully helpful for the world.
Maybe I can add my top list. So I like being an electrical engineer from the beginning. I like some of the things that are very promising prototypes. Like we have produced the world's fastest chip integrable photodetector based on graphene, actually faster than the measurement equipment could follow. So we don't quite know how fast it is. The magnetic field sensor by Bosch outperforms other competing technologies by a factor of 100. And if you have a factor of 100 in the prototype, you can afford to lose some in the manufacturing process where things are not as well controlled. But then something like the rear wing of an Airbus 350, where we have promised a prototype in a year's time, that starts to show that these things become real. You no longer need a microscope to look at the applications. That's top 3 from right now.
Perfect. So one question I have after hearing this is that, Dr. Reed and Dr. Weiss, you mentioned that the applications are still forthcoming. We're still learning what some of the applications of graphene will be. And yet, we've been hearing about graphene for many, many years. It doesn't show up in my everyday life, and yet, I'm sure it does that I don't know of. But I guess that's part of the point, is that I don't hear a lot about it in my everyday life. And yet, it's been around for a decade or more. It was part of the Nobel Prize. So this is tied into this question here from an anonymous attendee. What is needed to transfer graphene synthesis from the lab scale to commercialization? So what are the major challenges on this front? What is preventing the applications from going into industry at a faster rate? We're still seeing this emerging in industry. Why is that?
Yeah. Well, I think we're looking for demonstrations. You heard about a couple that are on the way, but as Evan said, how all this scales economically, what's the advantage for someone to manufacture something out of graphene, that's going to determine when there are applications that get in your hands. I would say graphene's still quite young. That a decade isn't so long on these scales, and we don't see new materials get into applications on this time scale typically. I think that's part of the reason for the very big investment in the graphene flagship in the EU, is to see if that time scale could be shortened. I think you don't hear so much about nano in things generally, and yet every phone, computer, device you have contains nano, and I expect that when graphene is in something, that may not be, that may not be as prominent as this is a graphene telephone. You're not going to see that. There will be components of things that'll take advantage of the properties of graphene and other 2D materials, and generally nanoscale materials, as they do now for many other materials. It's just not so broadcast that's part of the composition.
Okay. Why is, I like this question from Vartan. Why is graphene so interesting vis-a-vis creating materials for so many different applications in different domains? This is sort of calling out our theme of questions of all the different applications. What properties and behavior distinguish it from other materials? And in this context of its properties, where does the 2D nature of molecules rank in terms of importance or significance? Now, I would suspect that whether a material is 2D or 3D makes a huge difference, but I don't know how or why. Dr. Reed, you talked a little bit about the different materials that you can make these sort of 2D versions. So if you want to take this question, talking a bit about what the properties are that distinguish it from other materials.
Yeah, graphene is unique in a few respects. You could just talk about its optical properties. It was mentioned earlier that it has some unusual optical properties and that the absorption is relatively flat across the spectrum. But it's also, it's kind of, in some sense, almost more distinguished by the fact that it has certain combinations of properties. So it's a good electrical conductor, but it's also relatively transparent. It absorbs just a few % of the light that goes through it. And if you think about that for a moment, that's actually a relatively rare combination of traits. If you think about things that are good electrical conductors, it's usually, a chunk of metal or aluminum or something like that. You can't see through that. And that's a useful property for some applications, like in solar kinds of applications. You want electrical contacts that can conduct electricity, but allow light to go through at the same time. And so they're kind of specific applications like that might be useful. But there's also, as I mentioned earlier, there's a huge spectrum of other materials. And for a lot of things, you don't want a metal at all. You want something that is a semiconductor. And in the early days of graphene, there was just graphene. And so there was a lot of effort to try to make broad spectrums of devices out of graphene and kind of modify graphene to get the properties that you want. And my sense is that this sort of field of very thin materials is kind of growing up, and it's becoming like a lot of other materials fields where now there's a huge spectrum of materials to pick from, and the challenge is kind of finding the right material to use for your specific application. And so I think, if you're interested in optical communications, optoelectronics, you want to integrate something that emits light in your silicon computing device, I think there's actually a broad spectrum of materials now to pick from, which have the specific electronic properties that are conducive to doing that.
I think Evan put his finger on it, saying graphene was the proof of principle that you could make a single layer of materials, and it's still kind of the public face of 2D materials, but for any particular application, it may not be the best choice. And so we have this large and expanding range of materials that Evan and his community are helping to develop, and then we'll see how we can both produce those and what properties they have that we can use to advantage.
Great, yeah. So it sounds like we're going to hear a lot more from graphene and other 2D materials as we learn more about their applications, their optical properties, their electrical properties, their even magnetic properties. So that'll be interesting watching going forward. We got so many more questions, awesome questions. We are unfortunately out of time. We got a lot of great questions about, you know, applications, more application questions and batteries and electronics and what the cost is of graphene. So as a reminder, if we're going to forward questions to the panel, and follow-up questions can be sent to alumni.learn@mit.edu. So I'll repeat that again at the end. But on behalf of the Alumni Association, thank you so much to all the attendees for tuning in to the Faculty Forum online. Thank you again to our alumni panelists from UCLA, Stanford, and the Graphene Flagship. I know we didn't get to all the questions, but we'll forward them all to the panel. As I mentioned, you can tweet about today's chat using the hashtag MIT Better World. And again, follow-up questions or feedback can be sent to alumni.learn@mit.edu. Thank you again for watching.